Good morning, everyone. Can you show your video? Yes, yes, please. Thank you. Yes, because I'm not used to talk to a number, so I like talk to people. Okay, I will record my lecture start from today, but on the condition that we have enough students come to the class. If people say, hey, anyway, Professor Wu will record the lecture, I can watch afterwards, I will stop recording, okay? Because the purpose of recording is not for not attending my class. Is that understandable? Okay. All right, today I would like quickly review some of the very basic things about vectors. I know vector is not new to most of us, right? And then we should have chance to learn this concept in high school. But I try to quickly review it and put it in the content of electromagnetic field. Okay. When we talk about electromagnetic field, we know there's either electrical field or magnetic field. They are all vector quantities. So so-called vector quantities is a one quantity we can carry much more information than what we used to call scalar quantity on the contrast. So this is one thing. You see, a lot of physics quantities are vectors, okay? And also on the other hand, because dealing with vectors mathematically provide a lot of convenience. So therefore, we can define a group of, say, scalar quantity into a vector, right? And then it's much easier to process. For example, I can group our class of students as a vector, right? So this is a multiple dimensional vector, right? So why writing a program to you see a scoring and then attendance counting and so on, then I can just deal with this vector. Okay, here's it, right? So this is why people like to use vector. Okay, I still don't see another half of the students' video. Can you share your video? Yeah, I like to have eye contact. And also, can I see your video, not other people's photo, like other movie star or something? And I'm not interested in saying those movie star photo. Okay, so when we deal with, you see, vector also we deal with every day, right? So when we say we are driving a car, we know what the speed toward what direction, right? So that is a vector. So when we describe, you see, when the Hong Kong observatory station forecast typhoon, we first tell you what scale it is. So that's the magnitude, and also what direction of typhoon, right? So this is also a vector, right? And what I like to mention, you see, when we describe a vector, we used to use a bold face, okay, bold font, such as A. This is bold font. But when we write in bold font, is too much work, right? It's not convenient when we write a vector by hand. So we use hat, vector hat. That means this is a vector quantity. This is a different. This is not equal to ordinary A. Okay. When we have assignment or exam, if this is a vector quantity, I will ask you, you must write in this way. Okay. Otherwise, you will have a deduction because you couldn't distinguish vector and scalar, right? But when we deal with ordinary scalar quantity, we use ordinary form A, okay, without hat. So we must distinguish them. All right. So we said a vector has direction and magnitude. Okay, direction and magnitude. So here you see I have two vectors, vector A and a vector B. What is difference? What is difference? Okay, then for sure, the vector A, the magnitude of the vector A is smaller than magnitude of vector B, right? This is what I try to say if I sketch these two vectors, okay? And another information is they're in the same direction. In the same direction. Okay, in the same direction. So this is what I try to say. And then you may ask a question is, okay, this is I put A here, right? Then if I put the same, another vector, the same magnitude, same direction, but I put in the different location. Do you see these two vectors are the same? Say if this is a, let me show carefully, is another vector, same magnitude, same direction, okay? So that equal to the same magnitude, but I put in a different location. Are these the same vectors? Are the same vector? Anybody give me answer? Yes or no? Or wave your hand. I can say.
Nope.
Not the same vector. Not the same vector. I will say it's depend. It's depend. Okay. In general case, without specification, okay, specifically mention what that means. These two vectors is the same. I can put a vector here and the same vector here. You can put it in any way, okay, in any location, as long as the magnitude and the direction is the same. Okay, so vector has no specific position. Okay, we only have a direction and the magnitude, right? Okay, then let's look at the other two vectors. How about the vector C and the vector D? This is a graphic representation, right? What is a vector difference between C and D? Anybody give me a quick answer?
Reverse direction.
Yes. Basically, is C equal to minus D because of reverse direction, right? Okay, so great. Okay, let's move on. Right, we use vector to define a coordinate system. Particularly, we define orthogonal coordinate system. You see, the most commonly used one is a rectangular coordinate system or Cartesian coordinate system, right? And we use vector to define coordinate system. In this case, we use 3 vectors. We use vector A1. I will tell you what the difference between different head, okay? And then A2, I use triangular head, A3. Okay, I use 3 vectors to define orthogonal coordinate system. Okay, so in this case, okay, let me first mention what do I mean, okay? A head and a bar head. The difference is, so a head, when you have a triangular head, that means its magnitude. Its magnitude is always equal to 1. Then I call unit vector. Okay, I call unit vector. Okay, if I don't use triangular head, and this not necessarily, okay. A unit vector. Okay, not necessary. So when I have triangular head, I have a specific meaning. Okay, now let's back to this. I use these 3 unit vector to define a coordinate system. Then I have 2 options. One is using left-hand side, left hand. One is using right hand. So what does it mean? Say, if I look at figure 8, look at figure 8. If I use the right hand from vector A to from vector A1 to vector A2, some point to vector A3, this is right hand system. Then if you look at figure B, that is the left hand. That is from 1 to 2, then some point to 3, right? That is left hand, okay? And by universal, international, and past and future, people use right hand, okay? When we define any orthogonal coordinate system, okay, we use right hand to define coordinate system. This is we don't repeat this anymore, right? So this is how we define orthogonal coordinate system, but everybody in the world using right hand, okay, using right hand. Then from time to time we use unit vector. It's very convenient because it's a magnitude equal to 1, right? The unit vector. Then what we can do is, if I have a unit vector, this small a basically equal to unit vector, right? Then I can measure its magnitude of vector in terms of unit vector, right? So in this case, so vector A has a length of 5. That means they have a total length of 5 unit vectors, right? So I use unit vector to describe a vector. But however, you will say, in this case, you have to describe what is the direction of unit vector, right? Yes, of course, we need, right? Okay, now we know what is the definition of vector and the notations. Okay, now it's time, let's have a quick review how the mathematically manipulate vector. You said, oh, vector is convenient, right? Yes, vector is convenient because they are a systematic way mathematically to deal with vectors. Say first, we consider the addition. Okay, the addition of vectors, not necessarily just a single vector. You can have as many as you like. You see, so the vector addition. But if we understand if we understand how to handle two vectors addition, then we can handle how to deal with millions of vectors addition, right? Okay. For two vector addition, the rule, or not the rule, is a definition. What is the definition of two vector addition? Is if I have a vector B add vector C, okay, what definition is you put the beginning of a second vector, say vector C. This is or I can call this is tire, okay, and then put at the head or the end of the other vector. Okay, so let's suppose I have B. Then I have vector C. Then I place this vector C. Okay, I place this vector C in the way that because vector is independent to the position, right? So I put the end of vector C to the the beginning of vector C to the end of vector B. Or I put a tail to the head of other vector. Then I can draw another vector. Sorry, it's not straight. Okay, so this vector is defined as B plus C. This is definition. Definition is you couldn't derive a definition, right? So everybody, when we call vector addition, that is definition. Okay, you can manipulate this in different coordinate system. Okay, in different language, that's fine, but you must follow this definition. Okay, under this definition, that gave us a lot of clue to more conveniently calculate two vector addition, right? Now let's look at this. When we project, basically, if I have a beam of light illuminate toward axis A, okay, then toward axis A, then this is my projection. So the projection means this vector B, okay, vector B has a component in, has a component in vector A, right? And then if this is A, I can call it a component, okay? Then this vector C, if I have a projection, this is a projection, so the projection of C, this is a projection of B, okay? Then you can say the projection of B plus C that equal to projection of B plus projection of C, right? Right? So if this projection is toward axis A, okay, toward axis A, then you can project this vector in another axis. Okay, say this axis D, okay, this axis D. So you can do the same thing. You can do the same thing, right? So that means the projection toward the D, then B plus C, then equal to projection B plus projection C on the axis D. Okay, it's the same thing. So that reminds us, once I define two directions which perpendicular, one is A and one is D, perpendicular to each other, then I can add up the projection onto this axis. Okay, so in this case, let's say then we have this right-hand defined coordinate system, A1, A2, A3, right? Then I have a vector, I call this is a vector. If I call this your vector is a vector A, then if this is a vector B, which is called, you see, with a dimension of 6 times A2, then this vector will be A plus B, right? So then you can see I write in this way is A plus B, but this is not convenient to calculate. Yeah, this is just a symbol, right? Because I don't know what is direction of A1 and what direction of A2. And A1, I cannot simply add. I cannot simply add this. I don't know what is this. Okay. So I don't know what is this. Okay. Then at this moment, if I don't know A1 and A2, right? But if I understand A1 is perpendicular to A2, then I can manage to using Pythagoras theorem, right? I can use Pythagoras theorem because if this is A1, then if this is A2, okay, then this is 6 A2, this is 4 times A1, okay. Then I know what is the magnitude is. This magnitude is the magnitude of 4 times A1 plus 6 times A2. Okay, it's a magnitude, right? Then what is the direction of this is depend on the combined direction of this vector. Okay, we will talk about this later on, right? Now, this is the definition of A1 and A2. And also we have some clue is we can deal with the projection of the two vectors. So make this addition easier. So in this case, we find another more popular way to describe an arbitrary vector A. Okay, this arbitrary vector A is in terms of unit vector defined in a coordinate system. For example, we define unit vector X, Y, Z. Sure, it happens to be the same notation as we are familiar, like orthogonal coordinate system, rectangular coordinate system. All right. Then what AX means, AX is a projection of this vector A, the projection of this vector A onto the axis X. Let me put more rigorously, I put a triangular height, right? And then also this vector we can find the projection on y-axis, we call AY and AZ. So AX, AY, AZ, that is the projection on each unit axis. And AX, AY, these three projections are not vector. They are scalar, right? They are scalar. So we define a vector in a more convenient way is we define by its unit vector and its magnitude. Okay, and sometimes this is too much work, then we just use simply, we just use A without hat, or you don't have to use a ball font, right? Okay, so that is how we represent a vector in terms of projection. Now, let's say if we have multiple vectors, we like to calculate its addition, then easy, because we already observed, right? We can add up their projection on each axis. Then if we define vector A and the vector B, then this basically we add the projection on 3 axes individually, right? And then if we like to have a subtraction minus a vector, okay? If we like to have minus vector, so that basically is you add an opposite vector. Okay, we add an opposite vector C, right? A minus C. So in this case, we can find the projection. Okay, we can find projection on each axis. So this is how we handle. This is how we handle the addition. Subtraction is also addition. Okay, subtraction is also addition. Then now it's clear. When we call two vectors are the same, two vectors are the same, that means the magnitude are the same. Okay, the magnitude is the same, and the directions are the same, or the projection on 3 axes are the same. Okay, that is this relation. Right? This is so. This is what we call two vectors are the same. Right. Now, specifically, okay, in our EM field analysis, okay, then we need to define a special vectors. We use this all the time. The special vectors, what special vector not only used in electromagnetic field, also in some daily life as well. One vector is position vector. Okay. So we have a position vector. The position vector is relative to our reference point. Okay. For example, we define the origin of this coordinate is our reference. Okay. Then our position is defined with respect to this reference. Say, for example, you say this is a point P1. This is point P1. I like to describe the position of the P1. I just using vector. Okay, I just using this vector. R1. R1 refers to the position of the vector. Then same as position vector for P2. Well, I use R2. I use R2. So this position vector in a 3-dimensional space is unique, right? Is unique because each position is unique, right? Then in future, when we describe where I put my antenna, okay, then we have a reference. If this reference point is a universal station, then we can precisely use a vector to describe its position, right? That is the antenna. Then if I like to describe a point where I'm going to measure the field strength, this field is generated by the antenna near the train station. Then basically I define two position vectors. One vector position P1 is where my antenna is. And the position P2 is where I'm going to measure the field. Okay, I call field position. Right? Then I can define many other positions, right? Okay, so that is a position vector. In addition to position vector, then we also have another vector I call distance vector. Okay, this distance vector is to measure the distance between the two. This distance vector, so sorry, I use different color. This is a difference vector between position 1 and the position 2, right? And the distance vector we defined is P2 position vector, or I call R2. Okay, here. Okay, so its definition is R2 minus R1. Okay, R2 is this, R1 is this. Then it's clear, right? According to the definition of vector addition, R1 plus distance vector R1, 2, this is a vector, right? And I put the beginning of distance vector to the end of position vector R1, that's equal to R2. This cannot be wrong. This cannot be wrong because this is a definition of two vector addition, right? Okay. Then from time to time, we like to measure the distance. This distance is not only a magnitude or in terms of meters or kilometers, but also tell us a direction. Okay, that direction is pointing from R1 to the position of R2, right? So that is a position vector. And if you tell me, okay, you may say, hey, can I define the position vector as R1 minus R2? Can I do this? I have no reason to object it. If you use it at home, that's fine, okay? If you don't communicate with other people, that's fine. You can define in any way you want. But when you talk to people, okay, particularly in this class, right? When we discuss different formula or equations, okay, the theories, we all use this definition, okay, this definition. So this class doesn't accept, okay. So we have a position vector because we describe the field always related to the source, and then always is a vector. So we have to deal with a position or distance vector, this distance in terms of vector. All right. Okay. Any questions? Or you can type your question in the chat board, so then I can see it. So I really appreciate a student ask a question because the question you have very likely will be shared by other students. So when you ask a question, you're helping other people, right? So give me one question. So again, I still don't see many student video or face, even not a photo. Even I don't know, you say you logged on is a robot or a real person. So this Roam software is great, but they still have a lot of features not available. You see, at least we should have a feature to check if this is a robot, right? So one way I can check is to see this video. All right, let's move on. Or questions? Okay. So we just finished the discussion of addition. Then like quickly goes, what is the multiplication of vectors? Okay, we have two types of multiplications of okay. So if you don't have webcam, what I can say, okay, then we have a multiplication. We have two kinds of multiplication for two vectors, okay, for two vectors, and then we can have a multiplication for multiple vectors, but that is also sometimes we use. Okay, let's take a look of two. Okay, two vectors, and when people define a mathematical operator, say multiplication, addition is an operator, right? It's a way of manipulating two vectors. Okay, we must have a reason, right? We must have a reason to introduce it. Okay, nobody, you see, to do something for no reason, right? For no reason. Okay, so let's define the first multiplication we call a dot multiplication, or scalar multiplication, or dot multiplication. This is definition. Definition means when we have two vectors dot product, okay, A dot B, okay, this is solid dot, and the better show a little bit bigger dot, different from this. This is also dot, say A dot B. You didn't emphasize, okay? You didn't emphasize this is a vector multiplication. This has looks like no difference like this, okay? Because of vector, we used to use a boldface. Then we emphasize this, okay? We emphasize this with a little bit bigger dot, okay? Right? This is not good. This is good, okay? This is not good. So let's remove this. We use this, okay? So when we define dot multiplication, what we do is we use the magnitude of A multiplied by magnitude of B, then multiply a cosine, the angle between the two vectors, The immediate application we can think of this dot multiplication is to measure how much work you have done. If you pull a heavy object over a certain distance, and you have a force, you have a distance. This distance has a direction. This is the angle. And how much work we have done? Okay, the work we have done is the force times distance, right? Okay, this time is the dot product. Okay, but perhaps when we study in high school, we just emphasize, the magnitude of phase and the absolute distance of movement B, and multiplied by cosine theta, but not in a general way we represent. Okay, so in a more compact or abstract way, we measure this work done is using A dot B. Okay, A dot B. So you can see this dot product generally create a scalar, two vector dot product result a scalar quantity, okay, scalar quantity. And then they always, we can find a lot of physics quantities that equal to a two vector dot product, right? So the work done is one example, okay? Then according to this definition, this angle, both angle A to B or B to A is basically the same, right? If this is the same, then we can say A dot B equal to B dot A, not difference, okay? And then we call this commutative property. And also we can easily define, okay, how to graphically justify this. How to graphically justify this. If you have, say, if you have a vector A, vector B, vector C, okay, this is a vector B plus C, right? Then you graphically justify by yourself, okay? Then A dot B plus C equal to A dot B plus A dot C, okay? You can see if this is, say, I have another vector, vector A, okay? Then you can justify by yourself, okay? You can justify by yourself. So this is equal to this. You can justify graphically, okay? So now every time if I do this dot product in this way, not convenient. I have to measure the magnitude, I have to measure the angle, right? Not straightforward. I have to use a ruler to measure, not straightforward, okay? Let's find more straightforward way, okay? More straightforward way is, say, this angle theta A to B. If I have a vector A, if I have a vector A, vector B, okay, then this is the angle theta AB, right? This is equal to theta B minus theta A, all right? Okay, then very simple trigonometry equations. So everybody knows, right? Otherwise you won't sit here, right? Okay, then we can find, we use this trigonometry equation, we rewrite the definition, okay? We rewrite definition in this way is, I put vector A magnitude and vector B magnitude, put in front of its corresponding angle. A corresponding theta A, B corresponding to theta B, right? Same as the second term. Then you see, what is this? Let's look at one quantity. What is this? Is I have this, vector A, this projection in x-axis, this equal to its magnitude projection onto x-axis, right? So I call this, AX, basically vector projection on x-axis, right? So this term basically is this, right? Then same thing, you can understand this is a projection of vector B on x-axis. And this is a projection of vector A on y-axis and the projection of vector B on y-axis. Okay, we can easily justify, okay, when we calculate A dot B, if I know A, I can write as the projection. Then B, I can also write a projection. Okay, I first write it in this way, right? Then I can easily calculate. The dot product, okay? Dot product by multiplying the projection on x-axis and multiply the projection on y-axis and add them together, right? So this is what that tells us. Okay, what this tells us. Then also you can use this formula to justify this. Okay, this is another way, but I really encourage you to use graphic way to justify this distributive properties of addition. Okay, then having understood the definition of dot product, okay, then we can revisit. We take another look of orthogonal coordinate system we define using right hand rule, right? So basically in rectangular coordinate system, what we have is if we have x, y, z, okay, I define using right hand. Then you can say x dot x. That is itself. The angle is 0, right? The angle is 0. Then this equal to 1, right? This equal to 1, right? Because cosine 0 equal to 1, right? And the magnitude of each vector, unit vector with a triangular head equal to 1, right? So that equal to 1. Then how about x dot y? X dot y, because 90 degree, so 0, right? So every other, the dot product with the other unit vector equal to 0, and the unit vector to itself equal to 1. Okay, but this, I still, from this relation, I still could not say you are using left hand or using right hand. Be honest. We cannot say. So that means only have this dot product is not sufficient. Okay, it's not sufficient, right? Okay, so let's take a break for 10 minutes break. Okay. Okay, so let's resume our discussion. Some students write a chat message to me why we need to learn vectors. Okay, I don't know how to answer this question. First of all, we are not learning vector. We just have a very quick review, right? Because when we learn vector, we won't go that fast. We are go much faster. And the second is, I found our student lost interest in this course in the middle somewhere. Is because of the very basic things knowledge is very poor. All right, and well, I don't like to say some student because the weak understanding on some fundamental things, and then that cause the trouble later on. Okay, let's continue. The second vector multiplication, we call cross multiplication or vector multiplication. So its definition of a vector multiplication is I use cross to represent this is a vector multiplication. So what's it equal to? Okay, that first cross multiplication or vector multiplication result of vector. Okay, so this direction of vector is defined by right hand. So right hand rule is universal almost in every aspect in our content. So vector unit vector n define the direction of thumb. Okay, then the other four fingers is cross the direction of A cross B. The direction result is in n direction. The direction n is the thumb. And the magnitude equal to A times B times the sine, the angle between the vector A and the vector B. So right-hand rule also used to define our coordinate system as well. Okay. Then by definition, we can say A cross A must equal to 0. This is different from A dot A equal to 1, right? Equal to its magnitude square, right? So not equal to 0, but however, because this multiplied the sine angle, so A cross A must equal to 0. And A cross B equal to minus B cross A, this is understandable because A cross B and B cross A, so the sum point to the opposite direction. So we have a minus sign, right? And also you can graphically, you can justify. And the distributive property always also exists, okay? Then if we assume A and B, both A and B in the plane of, X or Y plane. Assume, okay. Assume A and B in the X or Y plane. This is a special case. I know this is a special case. Okay. Then we can graphically justify. Okay. We can graphically justify this. According to these trigonometry equations, we can justify A cross B. We can write in this way in terms of projection. Again, okay, projection of AX, AY, and BX, BY. Okay, the projection. Then, as a result, we can say A cross B if A and B all in X or Y plane, the vector product in the direction of Z. Right? And with a relatively simple formula, okay? But you may need to remember it. Okay? Or you can derive it by yourself. This is one way, okay? We have many ways that help us to remember it, okay? So in previous slides, I assume both A and B in X or Y plane. But if I have a vector in arbitrary direction, okay, not necessarily in X or Y plane, I can decompose into three, have to decompose and project on X, Y, and Z, 3 axes. Okay, so I can write A in terms of 3 vector component, 3 projection component, and B in 3 vector projection component, right? Or in another word, if you repeat this derivation on XOZ plane and YOZ plane, right? You can easily find, okay, just now we justified this, okay? We have justified. We have justified this. You can repeat this process. You can find, okay, the component in X and Y, okay, component in X and Y axis, right? Then the simple way to remember this relatively complex formula is using matrix relation, okay, using matrix relation. So we don't repeat this anymore. And also the distributive property for vector product also hold. Okay. Then from time to time we use product of mixed product. Okay. We have, say we have 3 vectors and the product, first I conduct cross product. Okay. I first conduct cross product. Then I conduct, because cross product result a vector. Then I conduct dot product. So this is called a scalar vector triple product. Okay. Then this product is interesting things is how I remember this is like you put A to this position, okay, then B to this position, C to this position. So you just rotate, okay. You keep the dot and the cross unchanged, okay. You rotate, right? So you rotate, let's say, so C become A, right? Then B becomes C and A become B. And you keep dot and the cross unchanged, put bracket. So this is this formula. All right. Then again, right, from this to this, again, so I rotate in this way, right? I rotate. So how I rotate is I put C in the position of B, okay, A to the position of, to the C, and the B position, put the position of A, right? And I remind this dot and cross and the bracket. So this is this relation. Okay, so this is how we can remember this. Okay, but the reason we use this, we can use this to prove many useful results. Okay, we are going to use in EM analysis. Okay, so that's why we mention this. Okay, this is a manipulation. And also there is a simple way, to do this calculation using matrix or using determining relation. So this is understandable. If I replace this by vector AX, so if this is a, say, X, Y, Z, so this is how we calculate this, right? Then what is the, if I replace this X, Y, Z by X, so that means I do dot product. I do this dot product. Okay, so this is also a way you can remember how to calculate. But from time to time, we found this relation is more useful when we want to derive some useful equations. Okay. Also, we have a vector-vector triple product. Okay, vector-vector triple product. And that means if we have a 3 vector, if you write in this way, I said, doesn't mean anything because this is incomplete expression. You didn't tell what is the sequence. Okay, so you didn't tell what is the sequence is, unless you do this. It's obvious, right? Because you say, if you have a different order, you'll result different things. Okay, you'll result different things. So the sequence for this is also very useful. And there is some simple way to help us to remember this is called a back cap rule. Okay, because ABC, so this is a back, this is a cap. You know what cap means, right? Okay, so this is also a way, this is what we call vector identity. And we use this vector identity, we can help us to simplify some derivations. Okay. All right. Okay. So this is this formula. I don't ask you to remember. Okay. There's no need. So there's no need. I just mentioned this. So whenever we use them, so you won't get surprised. Okay. You won't get surprised. So I don't do these examples, but however, you say what I try to say is this relation. Okay, so this is what I said. If you give A cross B cross C, this is wrong. Okay, this is wrong because you didn't specify the sequence. Okay, you didn't specify. So this is just give you a deeper impression. Okay, this is not equal. Okay, you must define either you calculate A cross B first or you can calculate B cross C first. Okay, that is the sequence. Also, this you see when people define a vector product, they must have some reason we need this operator. Okay, there's a one very important physical law we call Lorentz force law is if we have a charged particle movement put into a field that has static electrical field or static magnetic field. Okay, you will have a static electrical field, static magnetic field. Then that experience two forces on this charged particle, right? On the charged particle. One is the electrical field applied to this charged particle with charge Q, your experience the force that is electrical force. Okay, and also when the charge move, okay, when the charge move in this field, right? So you have velocity, or when we mention velocity, that means it is a vector. That means you have a direction and a magnitude, or speed. Speed is scalar, okay? Speed is scalar. Say, when you get a speeding ticket by the police, no argument in what direction you're wrong, you get speeding ticket, right? It's because it's just measured by the magnitude, right? It has nothing to do with direction. But when we mention velocity, okay, we have a direction, okay? So for this charge particle, then you have a magnetic force. This magnetic force is result of velocity cross multiply. The B is magnetic field flux density. Yesterday, we also mentioned we have another quantity called H. Okay, this we call magnetic So there is a simple relation between B and H, and then in when we talk about Maxwell equation, we will mention this. So both of them describe magnetic field. Okay, and also we can say there is also we call Hall effect. Okay, that means the force by the current going through a conductor while put into a magnetic field, we also experience the field, the force on it. Okay, so this is all. What I try to say is, yeah, flux. Yeah, flux density. Yes. Okay. So people ask, the B is the flux density? Yes. Okay. Oh, sorry. Yes, flux density. Yes. Then what I try to say is the vector operator. Okay, people use not only in the E field, in other field. Okay, all has a reason. Okay, why we use it. Okay, and also this bring us a lot of convenience. Right. Okay, then we also quickly review the coordinate system. We define a coordinate system using vectors, and commonly used orthogonal coordinate system. In our discussion, we talk about the three. Okay, one is a Cartesian coordinate system or rectangular coordinate system, and the cylindrical coordinate system and the spherical coordinate system. And these three coordinate system is about more than 10 orthogonal coordinate system that can be used for electromagnetic field problems. Okay, but the reason we don't need to study that much, or the reason people not using so many sophisticated coordinate systems, the reason is people less and less solving electromagnetic problem depending on the coordinate system you set. The reason is because most of the time we solve electromagnetic problem using computer, using numerical analysis, rather than classical closed form equations. Okay, then when we use numerical analysis, we really don't care what coordinate system you use. The simple, the better. Okay, because the reason we still pay attention to some other coordinate system other than Cartesian coordinate system is some kind of training. Okay, some kind of training. Right? Not necessarily we solve EM problem using other coordinates than Cartesian coordinate system. But still, you see, it doesn't hurt. Okay, we just have some training on how to use other coordinate systems. Cartesian coordinate system, I guess you say everybody is understand, right? So we define a point in a three-dimensional space using a particular coordinate system. This coordinate system we name X. We use X, Y, Z, and then those coordinate system doesn't change, okay, in directions, okay, and then perpendicular to each other, right, and defined by three planes. The intersect of x equals constant, y equals constant, or z equals constant. Okay, this three plane, x, y, z, three plane intersect to one point, right? Because two plane intersect a line, result a line. And the line intersect with a plane, result a point. Then that uniquely define a point. Okay. Let's move to a little bit more advanced topic is, okay, when we define a coordinates, when we define a vector, we already understand vector, okay? Only with those is far from enough for us to deal with electromagnetic problem, because we know the field are governed by a set of partial differential equations. So we have to deal with calculus. We have to deal with differential issues. All right. Okay. So to deal with differential issues, then we need to define what is the differential length. And also we need to define differential area and differential volume. Okay. I guess those concepts should be studied in your calculus. Have you? Have you learned, Yuxian, have you learned this in calculus, in engineering mathematics, differential length? It looks like nobody tell me, have you learned this? Okay. If not, I just assume not, okay? Then we look at this three-dimensional space, right? Then we define, we have a 1 point P. This P is just any point. Then this point has a very little movement away from the origin point. So this point moves to point Q. Okay, this movement is so small, okay, we call differential movement, okay? Then this causes the displacement in both X, Y, and Z direction. Then we marked by dx, dy, dz. Okay, then we have a distance vector. We have a distance vector. Okay, this distance vector I named as dl, which is a vector. This dl, I can say, I call it differential length. Okay, differential length basically is a vector. Okay, it's a vector. So I define this vector. I define this vector as dx in x direction, dy y direction, dz z direction. Okay, so this is differential length in Cartesian coordinate system. Okay, then this is still not down to earth, right? Not materialized. Okay, so it's you can use this for arbitrary point. What does it mean? What does that mean? Okay, so for example, you say we like to find the differential length along a curve. This is very specific, right? So if I have a curve, then I can give a point. I have a differential length tangential to the curve, right? Or once the point move to here in the different direction, okay, in a different direction. This is a very important property for us. Okay, for example, if we like to describe a magnetic field created by a current, I have a current flowing on this wire, this conducting wire. I like to find the point, arbitrary point created by this current, find a magnetic field created by this current. How to find this? We need to do the line integration current. But not only this, we need to deal with this integration, okay, along this aisle. So this is the background. We need to find differential length, okay. So okay, right? Let's take a look at one example, okay. This example, then if we define a curve, this curve is defined by x equal to y is a plane, right? X, y equal to plane. And on this plane, every point x, y equal to z squared. So we define basically like this curve. This curve. This is a curve. We like to find at a particular point, x equal to 1, y equal to 1, z equal to 1. Let's find what is dl. Okay, what is differential length? What is differential length? Okay, then how we do this is we just need to find a relation. We need to find a relation dx, dy, dz. What is the relation between them? What is the relation between them? In order to find this, then we can say if we take okay, we have this x equal to y equal to z squared. Okay, then if we take derivative with respect to x, then this equal to 1, right? So I partial this with respect to x. Okay, so that means x with respect to x equal to dx equal to dx, right? And then equal to dy dx, right? Then equal to 2z dz dx, right? All right. Okay. So then what we can find is dx equal to dy, right? You see, because from here I can find dx equal to dy, right? And then this equal to, if I divide, if I remove dx, then what I have is 2z dz. Then so basically this relation tell us we can find this relation. Okay, we can find this relation. So in this case, this is a definition. This is always true for no matter what problem is. Then we try to express dx, dy, express dx, dy in terms of dz. Okay, so we know dx equal to 2z dz. Okay, so I replace this equal to 2z dz then in x direction, right? And the second term is also 2z dz in y direction, right? Then the third term, because it's already in dz in terms of dz. All right, so in this way, I normalize this dx dy in terms of dz. Then I substitute z equal to 1, right? I'm looking at z equal to 1. So this result to this, right? Or in short, this equal to this. This is very clear. This is very clear that the projection at this point on z-axis equal to dz. You see this condition suggests you to express dx dy in terms of dz, because it won't say, because we won't say to having the projection on z-axis equal to dz, right? Okay, then this is a requirement. We can express the dl in terms of dz. Then this vector is specifically defined, right? This vector is specifically. This is the vector that define. Okay, this is a vector we can calculate. We can calculate the direction, we can calculate the magnitude. Okay, so this is how, for a given problem, how we find this. And also, we use the DL or the differential length, that can help us to define the normal direction of a surface. Normal direction of a surface. All right. So the normal direction, how to define normal direction of a surface is, if I give an arbitrary surface, okay, then I find two perpendicular curves. Okay, say we are particularly interested in the point, at this point, we like to find a normal direction of this surface. Then how to define it is, we find the two curves. The curve can be just arbitrary, okay? This is a curve exactly like what we've just found, the curve. We can find this DL1, for example, is this DL1, okay? If this is DL1, we can find DL1. And we can find another DL, the curve which is perpendicular to this curve. Okay, even not perpendicular is also fine. See, okay, you will say, oh, if you gave a perpendicular curve, I don't know how to find this. That's also fine. Okay, you find one curve and the arbitrary curve. Sorry, I should go through this point. One curve, and then curve 2 is arbitrary curve. Okay, then I find the DL1 and the DL2. And the DL1 cross DL2 must result a vector which is perpendicular to both DL1 and the DL2, right? And this vector I define as a normal direction. So this is basically define a normal direction, the vector. But however, I didn't stipulate the magnitude of this, because DL1, the magnitude not necessarily equal to 1, and the DL2 not necessarily equal to 1, the magnitude. So I normalize its magnitude, and I normalize the magnitude. So this vector must have a magnitude equal to 1. Do you agree? Do you agree? Right? Okay. So this is a general formula how we can find a normal direction. How we can find the normal direction of a unit vector. A normal direction of a surface. Normal direction of surface. Then if you say giving a surface, you can define two directions. One is towards this direction, one toward the other direction, right? Yeah, that's correct. That means if you like to find the normal direction of the opposite direction, fine. So you change dl1 cross dl2 to dl2 cross dl1. So you change the direction. So you change the direction. And also from time to time, we define a surface is a closed surface. Say if I have an object, we have inside and outside, right? We have inside and outside. Then in this case, when we define a normal direction of a surface, a normal direction of a surface, when we define normal direction of surface, we always say a normal direction point outward is a direction of our surface. Okay, outward, right? So we have one simple example. I just leave it to you to read. Okay, a very simple example. We define a cylinder. So what the cylinder is, if I only look at the XY plane, okay, so look at this equation. That defines a cylinder. That defines a cylinder, right? Because it's independent to that. Independent to that. This is a surface cylinder. So how to define surface? Say one x equal to 0. 1x equal to 0. Then y equal to the square root of 6, right? So 6. So when y equal to 0, when y equal to 0, okay, the x equal to square root of 3, right? Right, because 6 divided by 2, right? Take a square root, right? So that means, so we have kind of ellipse. Okay, this is a cylinder infinitely long along z-axis. So this defines a surface. Then that asks you to find the normal direction at this point when z equal to 0. When z equal to 0. When x equal to 1. Then at this point, so y must equal to 2. At this point, find its normal direction. Find its normal direction. Okay, so this is what this question, what this example about. Okay, so I leave it to you to read. Is that okay? So for this example, basically we need to find the two curves, right? Curve 1, easiest way, the curve 1, because this is a cylinder infinitely long along z-axis. All right, so find the point. The normal direction is this point. So the first curve, the easiest way to define the first curve, the L1, that will be, the vector is a straight line, right? So the straight line is along z-axis. So that means the straight line is x equal to 1, y equal to 2, right? That is arbitrary. So let's define, this is DL1, okay? DL1. Then you'll find another is DL2. on this plan. So this is how we discuss. We can find, we can measure the dy in terms of dx. Okay, we find the dy in terms of dx. Okay, then we can find the dl2. Then we use this formula. We can find the normal direction. Okay, normalize. We must normalize to magnitude equal to 1. All right. So having defined differential length, we can define differential area. For differential area, it's easy because once we know differential length, dl1 and dl2, then we can find the differential length according to this. Cross, okay, dl1 cross dl2, right? So for each surface in rectangular coordinate system, right, we have differential length in x direction is dx, in y direction is dy, z direction is dz. So we can find this is a differential area in rectangular coordinate system. Okay, then its direction is inconsistent with our x-y direction. So this is just for convenience, right? Because here you say for any small surface, you can have in 2 directions, right? You can have in 2 directions. So similarly, we can define differential volume. Okay, differential volume is the area dot multiplied by the height. Then this define a volume. And for rectangular coordinate system is easy. Okay, is easy. So that is dx times dy times dz. Then we quickly review vector and the basic operator of vector. And also using this vector, we define differential length, differential area, and differential vector volume, and also how to find the direction of differential length for a given curve, and how to find the normal direction of a surface. Okay, and also we use this general definition to find the specific expression in Cartesian coordinate system. Okay, but we still go too slow. Suppose all this material we should cover in 1 hour, but we use 2 hours. So, but I hope you see those concepts we very solidly built. Okay, then because we will use this all the time. So that's why you see we said this class is exciting because this is we intensively use the calculus we learn. Okay, if you didn't learn very well, okay, this is a chance for you to practice. So questions? So give me even just one question. Maybe some students still complain why we spend time to study vectors. So I don't know if those part is very well learned, and we don't need to repeat. So if we don't repeat, so we can skip the lesson 2. We come to lesson 3. Any suggestion? Okay, I will give assignment 1 this week. Okay, and then to practice those basic concepts. Even though you say this is irrelevant to electromagnetic field, but it's a very basic things for calculus. If you one day if you say, hey, I graduate from engineering, and then people may ask, oh, you must be very good in mathematics, right? So in mathematics, very basic things is calculus, right? And then now I give you a question to find the direction of a curve. Okay, this curve is not a simple straight line curve. All right, so we need to use those knowledges we discussed today. Okay, if no question, I remind everybody, you send a message in chat. Okay, type in your name first and your student ID. We use this for head count. Okay, we use this for head count. If yesterday we found not many students did this, okay, then sorry, so we don't know who come in that class. Okay, type your name first, then student ID. All right. Okay, great. Or if you don't like to type in public, you can type privately to the tutor, to Tan Xiao. Okay. Okay, so that's all for today. And goodbye.
Goodbye.